So today I'm going to talk about some of our work looking at leaching composition and microbial community with recycled concrete aggregate. This is some work we have been doing to try to control some of the runoff issues with RCA storage. I have to thank my co-authors who helped with this, and in particular, Maeda and Luthia are both of the microbiologist environmental engineers associated with this, and unfortunately they couldn't be here today, but I will try my best to answer any questions that might come up about that. So we've already talked a bit about RCA, but this is crushed concrete material that then gets graded for specific applications. The reason we use this, there's a number of reasons. There can be good cost benefits of this. There's sustainability reasons, and looking at specific design criteria. In terms of sustainability, the big contribution is really resource efficiency and trying to control how much natural aggregate we're using. For example, in Toronto, there's this great case study looking at how much concrete aggregate they really need over a 20-year period, and they estimated that they had less actual capacity than what they were going to require for concrete aggregates. And so in areas like this, where you maybe don't need the highest quality aggregate in a concrete, RCA or recycled concrete can start to offset that deficit as a material for use. It also helps with mining impact reductions. So, mining of natural aggregates is quite a destructive process. And of course, transporting of aggregates can pose a lot of CO2 outputs. So if you can do your RCA materials within a smaller transportation radius, you can save some embodied carbon. There are some design considerations when using RCA, of course. There's risk assessment issues of life expectancy and variability in materials. Strength requirements, we have plenty of research showing out there that we can get good quality strength and good quality durability for many different applications. And actually, in some applications, we can get better properties for specific items. But one of the concerns with using RCA are feasibility concerns. Do you have the right equipment? Do you have access to space to store your materials? And do you have access to the materials? One of the big concerns that comes around when using RCA is not only do you have a space to store it, but do you have a space to store it that runoff might not be an issue? And in most places, they're going to store their recycled concrete material outside. And so you have large stockpiles of material sitting outdoors, both before crushing and after crushing. Now, an RCA particle has this adhered mortar attached to it. And so this is a cement material, generally a Portland cement material. And as we all know, that's going to contain quite a bit of calcium hydroxide. And then we also typically don't have a lot of history on where that concrete is coming from, what sorts of chemicals it was exposed to, what other contaminations might be mixed in with that material. But when we're storing our concrete, we store it in a big pile. The clouds come along and it starts to rain. That water filters through that concrete and we get an effluent. Now that effluent water tends to have a fairly high pH, greater than 9. And as it moves further away, it will dilute and it becomes less of an issue. There's been quite a bit of research looking at dilution effect, but localized to your pile, your storage piles, you can have issues with nearby flora and fauna. You can damage underground utilities and pipes that might be more susceptible to corrosion. And then there's potential toxicity issues. And most of the time, in terms of water quality, the agencies are looking at the quality at the source, and so this effluent would then need to be treated. We were discussing this problem and talking about how the existing microbial community in concrete might be able to be used to buffer this pH runoff. There's been some research on the microbial community in concrete. I want to give a shout out to Julia Maresca, Dr. Julia Maresca from the University of Delaware, who has done quite a bit of this work. And a lot of the bacteria that exist in concrete can actually help to buffer high alkaline environments. And so if we can try to control that, we might be able to get less negative impacts from the runoff of the water. So what did we do? We did a laboratory study where we looked at two different sources of RCA. We had a laboratory produced source that had been stored indoors for its whole life, a normal 5,000 PSI concrete mix, crushed at 90 days and stored inside. And then we had a unknown material from a field source that was crushed from transportation infrastructure in New York City. We have very little information on where it came from, other than it was generally from somewhere in the New York City area, and that it had been stored in a stockpile in Brooklyn for an unknown period of time. So with our laboratory RCA, we crushed it with a sledgehammer and crushed it down with a jaw crusher to get 3/8 inch material. And we created some washed and unwashed samples. We also have a field RCA material that field RCA that came to us crushed using a larger scale jaw crushing system offsite. We sieved that out to get 3/8 inch material and created some washed and unwashed samples. So after that, we soaked our RCA for 672 hours in an enrichment solution. So this is a high pH solution that is looking to encourage growth of bacteria in this water or in this enrichment solution. And then from that solution, we can create what is called as an inoculation fluid. We then took new RCA and soaked that for 800 hours, either in the inoculation fluid or DI water, to try to figure out if this inoculation fluid could help us to control the pH of the RCA. We classified our microbes, and then we took the inoculated RCA, so RCA that had been soaked in that inoculation fluid, and soaked that again in deionized water to see if inoculating that RCA would help us to impact the pH changes on the system. And we also looked at the metals that might have been released during that process. So our original enrichment process, where we took fresh RCA and mixed it into an enrichment solution to create our inoculation solution, we saw two different really pH ranges here. The field samples had an initial spike of pH, a small initial spike of pH at early ages, and then long-term, the pH decreased to below 9. However, the lab samples kind of saw an increase in pH to around 12 and stabilized there. And so this is really indicating that the age of the RCA is going to have an impact on the pH of any solution that is going through it, mostly because, of course, stuff that has been sitting out and soaking, more of that calcium hydroxide is going to have leached out already, and so it won't have as much of an impact on the pH. We then took new recycled concrete, both washed and unwashed, and stored that in either the inoculation fluid or just clean deionized water. And what we found was that just storing those systems in either with inoculation fluid or not didn't have a big impact on the pH. A little bit of impact here in the long term with the field samples. We saw decreases in pH over time, but really there wasn't a big difference with the inoculation fluid for that. What we did see, however, is that the washing of the samples, or rather the inoculation fluid, did mobilize some metals at a higher rate than the systems that were not inoculated. And so that is a particular concern, because now we're actually releasing metals that we wouldn't have released before if we tried to create a fluid that is going to inoculate that system. We also looked at the bacteria that was formed during this, and what the real takeaway from this, since I'm sure many of you are looking at this and have never seen something like this, I certainly didn't. The big takeaway from this is that we, when we inoculated those systems, we really did see an increase in 2 of these bacteria that are highly tolerant to, excuse me, to alkaline environments, and also that can help buffer the pH. These heat maps show, we can see in the red that the type of, basically the type of bacteria that was enriched. And so we get a lot of halophilic, halotolerant, alkaliphilic, and anaerobic microorganisms. So basically bacteria that can grow under elevated pH and salt concentrations. So we're getting the type of bacteria that we would expect in this system. But where we really got some usefulness is that we took the RCA that had been soaked in that inoculation fluid, and we did what is called a and we called that being biostimulated. We took that RCA that had been biostimulated and we soaked it in deionized water for about 800 hours. We also soaked unbiostimulated aggregates, so ones that had not gone through that inoculation fluid. And what we see is that the systems that were biostimulated had a much slower pH increase of the soak water compared to the ones that were not biostimulated. So basically, when we biostimulate RCA in some way, or increase the growth of that alkaliphilic bacterial community, we can slow down the leaching of calcium hydroxide, or buffer the solution that's coming out. And so this is important for us, because typically in the field, when you've got a stockpile, the water is moving through it rather quickly. And so with this is showing that the fast movement of water will not have time to see significant uptake in pH. So these systems, if we can biostimulate the RCA before it gets stored, we can actually reduce some of the impact of that runoff. We also saw that excuse me, lower levels of metals were leached out of the biostimulated RCA. So in summary, mixing inoculated solution just into the RCA doesn't really impact the levels of pH during leaching, but that inoculated solution may increase the metals that come out. However, soaking RCA that has been biostimulated will see slower pH increase and have reduced levels of metals leached. So what does this mean for us? Basically, if we can find a way to biostimulate that RCA, we might be able to prevent pH changes as water flows through stockpiles. But this biostimulation process is not really viable for use in practice at the moment. We need to find a way to do it quicker rather than having to soak the aggregates for a few days before it's viable, because that's not really going to be useful on a large scale. But we can try it. We're looking at ways to improve that biostimulation method as we move forward. So I want to just acknowledge real quick our department that helped fund some of this work, and then material suppliers for some of the materials we made. This work is currently under review in the Journal of Hazardous Materials. And I think we might have a couple of minutes for questions, but otherwise you can email me at adams@njit.edu.
Matthew, we just have one question left here. How much biostimulation you think we need to like a big pile of RCA?
Right, so that's a big question. I see that question here from Engage. So that's a big question still. You know, we soaked our aggregates for a couple of days for this sort of initial study. In terms of how fast can we actually do it and see results, we need to do some more work and look at many different timelines. This was sort of the initial pass-through proof of concept idea. And so we only did that one soak time. So that's still a big question out there.